It's my great pleasure to introduce this afternoon's first speaker, Anna Sakovich. So since when she was a graduate student, I've been following her work greatly, and I'm really a big fan of her work. And today she will talk about the mass aspect function for weakly regular asymptotic hyperbolic manifolds.
Thank you very much, Lan, for the introduction. So I would like to start by thanking the organizers of this very nice conference for preparing it and organizing everything. It's really a great meeting and a great occasion. Yeah, it feels very special to be here and to be invited to give a talk here. So I would like to start my talk by congratulating Yvonne once again on the occasion of her birthday. And unfortunately, I never met her in person, but yeah, I have a little private story to tell you. When I started my PhD at KTH, so it was around year 2008. So it was actually, so my advisor gave me some papers to read over the summer, like, before starting my first project. I don't actually remember what the other papers were, but but this paper was very important. So I kind of, when I came to do my PhD, I didn't even know that I'm going to do a PhD in mathematical general relativity. I knew it will be something related to differential geometry, but not MGR. But I kind of immediately liked this paper and topic, and I actually went on and wrote a paper about something similar. Yeah, and then so this paper is about constraint equations written by Yvonne and also Jim Eisenberg, who is one of the organizers and who is also a very dear person to me. So later on I moved away from constraint equations, but it's like in this field, no matter where you go, kind of everywhere you feel Yvonne's legacy very strongly. And one more thing is that, being a female mathematician, I feel very privileged to work in a field which has been pioneered by a woman. I think I would like to relate to Zoe's talk yesterday that actually we have a quite good proportion of female mathematicians in our field compared to others. So I think it's because of Yvonne also. And yeah, I would like to thank her for being a very great role model to all of us female mathematicians and a source of inspiration. Yes, so now I'll move on about my talk. You probably have forgotten the title. It was a bit lengthy introduction. Yes, I'm going to talk about the mass aspect function of asymptotically hyperbolic manifolds of low regularity. So I will briefly tell you what is going to happen in this talk. Historically, there are two definitions of mass of asymptotically hyperbolic manifolds. They are both quite new compared to EDM mass, like from early 2000s. And then one definition is the definition of Xiaodong Wang. It is based on the notion of conformal compactification. So you think that your asymptotically hyperbolic manifold is something similar to the Ball model of the hyperbolic space. So in a sense, you have some kind of boundary at infinity. And then this mass aspect function of Xiaodong Wang, so this is kind of his definition of mass. So this is something you have at the boundary at infinity. This is some geometric object. Then there is another notion of mass. This is mass function of Chruściel and Herzlich. It is more similar to the notion of ADM mass. It's more in the style of ADM mass definition for asymptotically Euclidean manifolds. These two definitions, they have a big overlap, so they agree to a certain extent, but then each of them has something extra that the other one doesn't have. For example, so definition of Chruściel and Herzlich, it applies to very general class of asymptotics, like the most general you can imagine in the context of mass. Wang's definition is more restrictive in this sense, but it captures this geometry at infinity. So this mass aspect is some invariant on the conformal boundary. And so in our work with Romain, we kind of try to unify these two approaches. So what we have been looking at is defining mass aspect function itself in the ADM mass style. And so I'm going to tell you how this can be done. So the idea is, also we would like to have very general asymptotics, of course, like in Chruściel and Herzlich work. And we would like to have very low regularity, as low as possible. So our first step will be to define mass functional and low regularity. So we will basically modify Chruściel and Herzlich definition using cutoff functions. After that, we will be able to define the mass aspect function itself as a distribution on the sphere at infinity. And for this, we will plug in, so this mass function of Chruściel and Herzlich, so you plug in into it certain functions for computing the mass. And so we will be plugging in functions which are like a bit kind of larger class of functions that we will use for plugging in, and this will allow us to define mass aspect function as a distribution on the sphere at infinity. And then in the end, we can show that our definitions, they have good properties when you change coordinates. So we have some kind of covariance in the style of Robert Bartnik that Melanie has alluded yesterday to in her talk. Yeah, in the very end, I will maybe say just a word about how this could be used in the context of positive mass theorems. Okay, so this is, I just wanted to tell you very briefly about kind of the difference between ADM mass for asymptotical Euclidean manifold and the mass of asymptotically hyperbolic manifolds. Well, the kind of the thing is that, ADM mass is a number, asymptotically, as you have seen in the first slide, so asymptotically hyperbolic mass is a functional or a vector. And so the idea is that, definition of asymptotically Euclidean manifold, so you saw yesterday in Melanie's talk, for example, asymptotically hyperbolic, you will see in a while, but the idea is, you compare your manifold to a model background in a chart at infinity, and you also define mass kind of by comparing manifolds to the model. Because mass and general relativity comes from considerations similar to Noether's theorem in classical mechanics, so you need to take some dynamical aspect into perspective. And the idea is that you view your model data like hyperbolic space and Euclidean space as slices of some model spacetime. So here Minkowski fits perfectly well. So I mean, you can think, okay, you have your Minkowski. Something I need to turn on. Yeah, so you have Minkowski, then you have Euclidean spaces, T0 slice, and init. So this is the axis, and then you have hyperboloid sitting here also. Make this circle blue. So this is so hyperbolic space is unit hyperboloid, like a sphere for Minkowski. Now, so like from these considerations related to Noether's theorem, so mass comes from these isometries of background spacetimes, Minkowski, which preserve your model data, so kind of they act on your model data by isometries. At the same time, they should generate some motion in time. And so if you look at Euclidean space, the only thing we can do with it, we can just translate it up parallelly. That's, I mean, if you boost it to something, so it's not Euclidean space anymore. With hyperbolic space, we have much more freedom, so we could translate it up, but we could also boost it, because boosts are like rotations for the sphere, so they, so like, for example, they will keep this hyperboloid in place, but they will reshuffle the points, so maybe this blue circle become this circle eventually. So kind of, so in asymptotically Euclidean case, you have just one thing you can do, this translations in time, but in with the hyperboloid, there is a translation in time, and then there are n boosts each, like in direction of each spatial coordinate axis. So this is why you think of mass mass usually as a functional, like on some n+1 dimensional vector space. So you can think it's a vector of n+1 components. Yeah. So the difference is that it's much more complicated object than asymptotically Euclidean mass. Okay. Oh, I forgot. Yeah, I'll try to take care of myself. Okay, so this is our model of hyperbolic space. So I will, because we are interested in this conformal boundary, so I will be using the ball model. So, well, then the hyperbolic space is just the unit ball in Rn, and then, well, the metric is conformally compact. So we have this function rho, which vanishes exactly on the boundary of this ball. And then we rescale the Euclidean metric on the unit ball by the inverse power of this function. And in this way, kind of, the boundary will be at infinite distance from every point. So you can speak of this like as conformal infinity or boundary at infinity. And then the definition of mass is done. So we said the mass is a functional, and it is as well, what you plug into this functional are solutions of this equation. So they appeared in Lorenzo, Stock-Lorenzo called them lapses. I will do the same thing. Well, this is an over-determined equation, but it has solutions on, for example, in Euclidean space and hyperbolic space. So in hyperbolic space, it is n+1 dimensional, so it's spanned by these functions. So rho is this conformal factor which vanishes on the boundary, and then x1, xn, they are just coordinate functions on Rn. Right, so now I can give you the definition of Chruściel and Herzlich mass functional. First I need to define asymptotically hyperbolic manifolds. So this is definition as it appears in Peter and Mark's paper. So we have complete Riemannian manifold, metric is of class C1, uniformly equivalent to hyperbolic metric. So we will call it asymptotically hyperbolic if there is a diffeomorphism from outside of a compact space in our manifold to the outside of a compact set in the hyperbolic space. And then, so we require, so this is like minimal assumption essentially for the mass to be well defined. So this kind of in terms of follow-off. So this is like saying that this difference between the metric and the hyperbolic metric computed in the chart, so it lies in a certain weighted Sobolev space. So it's like W12 with weight 1/2. But yeah, so what it means, like, yeah, if you want like pointwise, this is this decay roughly. Well, and then for like if this kind of correction E difference between the metric and hyperbolic metric, so if it satisfies this, yeah, if this quantity is finite, well, then we can define the mass functional. So the mass functional is, so this is very similar to ADM mass. So this is a flux integral. So kind of R equals 1 corresponds to the sphere at infinity. So R kind of goes to 1, we go to infinity, we approach infinity, kind of using spheres. And well, so it's linear in E, and then we plug in these functions V, which are these lapses that we had on the previous slide. So interestingly, if you plug in function V equals 1, you will just recover ADM mass. And this is just reminiscent of the fact that, well, both formulas come from the same thing. They both come from linearization of scalar curvature. So you linearize scalar curvature and you integrate it against a lapse function. So you will get this as a boundary term. And so you can use this fact, and if you require some more kind of, if you impose an extra condition on scalar curvature, some integrability condition, so it's like saying that, well, scalar curvature minus scalar curvature of hyperbolic space times the lapse function should be in L1. So then you can show that this is something well defined, something finite. Also this mass functional, it has good covariance properties. So when you change the chart, so it changes as it should. So we'll talk a little bit about it in the end. This is definition of Xiaodong Wang. So we assume, so let's assume the manifold is asymptotically hyperbolic, but now we impose much more restrictive asymptotics. So we assume that in the chart of infinity, so this kind of correction E difference between the metric and the hyperbolic one, so it has this very special form. So at the leading order, it is some smooth tensor, which is smooth like up to the boundary on this unit ball. Well, it is also required to be transverse. So like whenever you plug in radial direction into it, it should vanish. So yeah, it comes with the power n. So with this, if you compute the norm of E, you will get O to order of rho to the power n. So this is much faster decay than on the previous slide, and this is kind of the borderline case. If you increase it a little bit, then the mass is zero automatically. So so what happens if we use this asymptotics and we plug in like this basis of lapse functions into it? So if we kind of try to compute Chruściel and Herzlich mass functional for this asymptotics, well, what we see is that the mass is completely defined by the trace of this tensor that we have here in the expansion on the boundary at infinity, and this trace is what is called the mass aspect function. So the mass is completely encoded in the mass aspect function. So interestingly, so mass aspect function is a geometric object. So the mass aspect itself has covariance properties. So if you, for example, boost your coordinates, it will change by a conformal factor, and the same applies to this kind of correction term. So this E bar is called mass aspect tensor usually. So all this, I would like to bring this paper to your attention. So it's where mass aspect function was studied in great detail. So paper by Chruściel and Gicquaud from 2016. So in particular, these covariance properties were discussed and so on. So there is one more definition of mass, which is very interesting for some reason, for various reasons. So one reason is, for example, so this is this definition using Ricci tensor, as people usually say. Well, this definition goes back to very old works by, for example, Ashtekar Hansen and Piotr Chruściel also, but I think it's really Mark Herzlich who in 2015 kind of showed that this is this is a well-defined quantity here, and he kind of related it to mass functional of Chruściel and Herzlich, for instance. So what is appealing here is that you have you had this strange first order derivatives of the metric on the previous slide, and here you have something very geometric. This is like Einstein tensor, and but it's still like it's not clear that it's coordinate independent from the beginning, because you plug in this x here, and this x is something you take from computing in your chart. So what is this x exactly? So this x is a conformal killing vector field, which is not killing, so it satisfies this condition. So the derivative of b is like divergence time b up to some coefficient. So what relates this formula to the mass function of Chruściel and Herzlich is that these conformal killing vector fields, they are like kind of aligned with lapses. So if you compute the divergence of this conformal killing vector field, you will get a lapse up to a constant factor. So then the idea is that you can you take second Bianchi identity and you integrate it by parts against conformal killing vector field, and then you can relate this to formulas like this is how they are related. So this is H tilde is this Ricci definition, and H is Chruściel and Herzlich mass functional. So let me again remind you of our goals, what we want to achieve. So we have seen there is this mass aspect function, and there is this ADM style definition, and we want to kind of put all this together. So we would like to define mass aspect function in ADM style and in low regularity. And for this, we basically are going to follow the following steps. So first of all, we will kind of define mass functional and low regularity. So regularity, like on the local level, is W12 intersected with L infinity log. So we are going to redefine the mass functional using cutoff functions, kind of in the place of this unit normal. You will see it in a second. And then, as I said, we are going to use this definition. We are going to allow a bit larger class of a larger class of functions than just lapse functions. So this is how we will define mass aspect in the end. So it will be a distribution on the sphere at infinity. So this is so this is what we had when it comes to asymptotics of Chruściel and Herzlich. So again, a metric uniformly equivalent to the hyperbolic metric, E is in the same weighted Sobolev space as before. So this is what exactly it means. So this is the same integral as was on the slide about Chruściel and Herzlich mass functional. The difference is that we no longer assume that G is C1. So in this case, scalar curvature is only defined like in the sense of distributions. We will see kind of a formula which shows which gives ground to this later on. This is a bit similar to work of Lifloch-Mardaria. So this is like defining scalar curvature as a distribution in this regularity, and then also the whole thing, this defining of the mass functional low regularity, so it has some similarities with what Dan Lee and Philip Lifloch did in the case of asymptotic Euclidean manifolds. So they do it a bit differently. So we are going to work with cutoff functions, and they are still using like this R coordinate. So this is a bit different approach. Well, we will additionally impose this assumption. So this scalar curvature plus minus scalar curvature of hyperbolic spaces in this weighted Sobolev space. So kind of we again want V times this to be integrable. In this regularity, if you look back at the mass functional, it doesn't make sense anymore. So you can speak of trace of E on the hypersurface, but these derivatives are not, they are defined only almost everywhere. So on a hypersurface, you don't know what happens to them. These terms are ill-defined. So we need to do something with them. The idea is that we are going to use cutoff functions. Maybe I'll draw them here. So this is like the family of cutoff functions we are going to use. Okay, so this is my interval 0 to 1. This is a hyperbolic space. So, the boundary is somewhere there. Okay, so then we have this compact set K outside of it, which we have our coordinate systems. Okay, it's not covered by this chart at infinity. So the cutoff functions look like this. Okay, one is so high. Yeah, so they all we vanish here kind of on K, and then it will go up. Then it will go down. So there is some set on which this function is 1. So we call it omega k. And this is this cutoff function Ck. So what we require here is that so they vanish on this set. I'll draw one more function perhaps. Maybe I'll make it yellow still. So they all kind of will go like this in the beginning. I mean, they are defined in a bit kind of more difficult way than I put it on the slide. So the idea is that this kind of set on which the function is 1 that should grow, get bigger and bigger, and then if I take the union of all these sets, omega k should cover kind of the neighborhood of infinity. Then gradients should be uniformly bounded. And this is pretty much all we need to assume. Yes. Yeah. So decay rate is it's this kind of the decay rate. So it's still the same. So rho to tau is greater than n over 2, like in Chruściel and Herzlich work. Yeah. So this, like, everything is the same as in Chruściel and Herzlich except for okay, I don't see the pointer. Except for this integral in there. Sorry, except for the metric is not C1. Yeah. Okay, let's see. Yeah, no. No wonder I didn't see it. Okay. So decay rate is as for Chruściel and Herzlich the same. Okay, so so now we can okay, it should be L infinity. So like regularities on the previous slide, and we now redefine this mass functional as follows. So the idea is that we no longer work with surface integrals, but we work with like bulk integrals. And we replace this normal to the sphere by gradient of this cutoff function. So this condition of the scalar curvature, it helps us to show that this defined in this way, this kind of new mass functional is well defined, and it doesn't depend on the sequence of this cutoff function. So how we choose it exactly. And also we can connect to the definition of Chruściel and Herzlich. So if the metric is C1, as in their case, so yeah, this new definition and the old definition, they agree. It's the same. Right. So let's see how. So this is just the idea how we show it. Yeah, it's exactly the same idea how you would do it in the smooth case. So the starting point is right in the first variation of scalar curvature, which Jean-Philippe Bourguignon showed us on Tuesday. But we write it a bit differently. So he had this Laplacians there and Hessians and so on. But yeah, we really wanted to be like, we want to collect all this leading order derivatives into a divergence. So this is kind of motivates this distributional characterization as well. And so in the smooth case, you would integrate it against the Laps function V, but here we integrate it against Laps function times the cutoff function. And then you perform integration by parts. The only thing one needs to be careful with, we want to maintain this correspondence between the gradient of the cutoff function and the normal to the sphere. So we don't want to introduce any like second derivatives of Choquet. So, and of course we fundamentally use this Laps condition because this is what is also used when you just define mass of asymptotically hyperbolic manifolds or ADM mass. So you really need to use this Lapses. Okay, but as it turns out, so if you inspect this argument on the previous slide, you actually don't need to work just with Lapses. You could allow more general functions, and everything will still be well defined and like independent of the sequence and so on and so forth. So you don't need to just take this from this set. But you could have like order row here instead on the right-hand side. It will still work. But okay, let's kind of try to make this set a little bit more structured. So kind of we can split this equation into like pure trace. So pure trace is this. So we say, okay, let this trace be 0. So this is like a nice elliptic equation, which is well understood. And then we have this, okay, and trace-free part, we say, okay, it falls off like O to rho, which is like this admissible order. Well, we need to assume a little bit more kind of fall off here. So we assume now slightly more. So we assumed before like n over 2, but now, 1/2. So sorry, not n over 2, 1/2. So in dimension 3, we get some additional assumption on fall off that we need here if you want to use like these more general functions. So kind of this approach, like using this more general set of I don't know what this should be called, generalized Lapses maybe. So this kind of allows us to define mass aspect function like in the ADM style. And so this is the theorem how exactly we do it. So we start with a function. So V0 is some function on the sphere at infinity. And then, we solve this PDE, which is like very nice, very natural in the asymptotically hyperbolic setting and very well understood. And we solve it with the following kind of boundary data at infinity. So it kind of, yeah, if we multiply our function with rho, so it should be this prescribed value v0 on the sphere at infinity. Just maybe a little comment on solving this. So regularity here is such that we can't kind of rely on standard sphere, which is, for example, in Lee's monograph about asymptotically hyperbolic manifolds. Because we don't have like elliptic regularity in C0, but we use like really computational approach, which only works in hyperbolic space. So we construct this like Poisson kernel for this asymptotic Dirichlet problem, and so solution is a convolution. And then for this constructed solution, you actually can show that this you get this decay for this quantity, which you need to follow for things to be well defined. So kind of, yeah, we can in a sense associate any function on the boundary at infinity with some generalized lapse. So a function like this. And then we can just use it for defining the mass aspect function. So we just say, okay, mass aspect is a functional. We plug into this a function on the sphere at infinity, and what we need to compute is the value of mass functional on the related generalized lapse. And it turns out that so one can show that this map is continuous. And also, if we assume that our asymptotically hyperbolic manifold is satisfies the assumption of Xiaodong Wang, then we actually recover kind of his definition, because his definition is about like integrating functions against the mass aspect function. This is what this functional does. Rho. Sorry, rho. Yeah, exactly. So the one you use for this conformal factor in the conformal compactification. Yes. So you know these functions they will this Boole model is a bit inconvenient, but they behave like rho to -1 maybe so we saw it on the first slide. So they are like x. So this basis was like xi divided by rho, and then 1 minus rho over rho. So you know, like, okay, you could prescribe it to be xi, yeah. Then you get v, and kind of you're back exactly to Wang's integrals that he had. Yeah, exactly. So it's about asymptotics, yes, because I mean they grow at infinity. Well, in other model they would like grow exponentially. Yeah, so you really like prescribe the asymptotics here. Right. So maybe also actually one can also define mass aspect function using Ricci tensor. This is maybe, I don't know, maybe it doesn't have so the problem with this Ricci approach, you really need quite a bit of regularity here, because it's just because how it's defined. So I'll just show how you could define mass aspect like in higher regularity using the same approach basically. So the idea is, again, so we had this definition of mass using like Ricci tensor, and what we plugged into it were this conformal killing vector fields. So we had this X on this place, but then again, the idea is that for this to be well defined and related to the mass functional, you don't really need to plug in conformal killing vector field, but you could plug in something which behaves like this, so this quantity doesn't have to vanish. It just has to follow fast. Do you have a question? Say it again. Yeah. No, it's not needed. No. No. No, so asymptotics are like for Chruściel and Herzlich. But there's a particular case in Wang's asymptotics we recover his definition back. But yeah, so the idea is just now we want kind of masses, some quantity on the conformal boundary. Yeah. So yes. So with this, So instead of so basically we could use not a conformal Killing vector field, but something which satisfies this property. Yeah, actually, kind of gradients of these lapse functions work very well. So they exactly kind of satisfy this, and so you could plug in them instead of this conformal Killing vector field. So kind of the definition would be the same. So you pick up V0 and then you solve this, and well, you plug in the gradient of the related V into this equation. Yeah, so yeah, now maybe I'll tell you a little bit about kind of whether all this that I've been telling you about if it's like if it behaves well if we change the kind of our asymptotically hyperbolic chart at infinity. So let's see, we have a right here. Oh, no. Okay, I won't touch anything. I'll go here instead. Yeah, so this is like about how this new mass functional, this modified mass functional behaves under the change of coordinate chart infinity. So it's like a very standard problem if you would like to show that the mass is a physical quantity, so that it doesn't depend on the chart at infinity. So yeah, I'll just maybe draw some diagram which illustrates the whole thing. It's like so this showing kind of coordinate covariance or coordinate, well, which is like analog of coordinate independence in this case. Yeah, so the picture is like this. So we have our asymptotically hyperbolic manifold. So I'll write M minus K. So K is this compact set in the inside. Yeah, maybe not. Yeah, so you have this like region which is covered by the chart at infinity. So in principle you could have two charts, like call one phi1, call the other one phi2. And okay, these both charts will take you to hyperbolic space. So hyperbolic space, I'll also use the ball model as before. We have xn, x1, and then we have this two balls sitting here. Yeah, and then it's outside of a compact set here as well. So this is like hn minus. Yeah, I'll assume slopily that it's the same compact set in both cases. Yeah, so we have two charts. They take us to the hyperbolic space, well, the question is like, okay, if I use either chart, kind of how mass functions related in them. So and this is like usually it's a two-step process, like keeping track of everything. So first step is asymptotic rigidity. So the idea is that basically we would like to understand the transition map between these two charts. So let's call this map phi. So okay, this is phi2 composed with phi1 inverse. Yeah. So what you would like to show in this case is that this is something close to an isometry of hyperbolic space. Yeah, and then So it could be some kind of boost, which is far from identity. So maybe I would like to represent it as a boost and then composed with some phi 0. So this A is a boost. And this is something asymptotic to identity, like almost an identity. Yeah, and this is like first step is understanding this transition map and writing that this is exactly what we get. So well, on the slide you can see, well, usually, for example, you would represent this. This phi 0, for example, you would usually write it as an exponential map of at x with respect to some kind of small vector field psi, which decays fast enough. So one step is understanding this transition map, and the other step is okay, once you have established the splitting into a boost and a part asymptotic to identity, so you would like to show that this is only the kind of the boost which will show up in the difference between the masses, and this part asymptotic to identity will not show up. So this is how you expect mass functions to be related when you to each other when you change the chart. So yeah, and let me. Okay, I'll get back to the board in a second. So here, this step, we kind of assume a bit, we need to assume more regularity here for showing that the mass changes as it should. So, well, kind of one assumption is, well, because we need some Sobolev embedding to hold, so well, this is this Q greater than N Sobolev space here that we would like to have. Then we have this other condition. So this condition has kind of an intrinsic interpretation. So basically, you would like to tell solutions of a certain geometric PD on your manifold apart from kind of corrections which come from other things like difference of the metric and hyperbolic metric. So you will see this appearing soon. So I would like to say that this argument is very that we use. It's very similar to the argument of Bartnik from paper of 1986. This is where he used harmonic functions that Melanie was talking about. So the idea is essentially the same. We just kind of find the good replacement of harmonic functions. And also the argument was actually in the smooth case, so not in low regularities we have, but if you assume everything smooth. So there was a sketch given in the paper of Herzlich in 2005. So he has some conference paper, which is a very good overview of asymptotically hyperbolic masses. But yeah, so we can't really do the same thing as he does, because he can just kind of analyze ODEs in radial direction. But we need to work like with kind of bump functions and integrals. So it's technically much more complicated. Yeah, so well, maybe I'll tell you just right. I guess I have 5 more minutes, right? Yeah, good. Yeah, so just the kind of the idea how we kind of get this identification. So you have yeah, so on the hyperbolic space we have this special lapse functions that we have seen. So well, let me call it like V0, the first function. So it's 1 over rho divided by rho, and then we have this VI's, which were like xi divided by rho. Yeah, so we have exactly the same functions here. V0, VI's, yeah, I from 1 to n. Also I from 1 to n. And so, well, what we will do, we will bring back these functions to the manifold M. So I like using my 2-coordinate system, so I construct some functions on MG. So well, I call them X, like X, not curly X. Curly X I will use for something else. So let's call it XA. Well, XA is well, this is VA composed with phi 1. So A is from 0 to n. Yeah, and I construct the same. And these ones I will bring back using phi 2. So I have x, I will call them ya equals to v a composed with phi 2. Yeah, so these are not very geometric things, so we kind of constructed them using the chart. But what we can do, we can promote them to a solution of geometric PDE, which is similar to this equation satisfied by general lapses. So I kind of use these functions to construct functions. I'll call them curly x, curly xa. So this is a function which at infinity it asymptotes this xa, which I got using my chart from these functions over here. Well, it solves the PD Laplace. I don't know what's right here. Maybe x plus n x. Yeah. So this is my equation for like generalized lapses. Yeah, and I do the same thing over here. So some curly ya, so it asymptotes this ya at infinity, and it solves, yeah, same thing. And now, so the thing is that so I mentioned this geometric condition on the dimension that we have imposed. So under this condition, the space of solution of this equation is intrinsic. It's an n+1 dimensional space. Well, on the one hand, it will be spanned by these functions. On the other hand, it will be spanned by those functions. And also can kind of equip this space naturally with a Minkowskian norm. So it will be like going from one orthonormal basis to another one. So we'll get a boost in this way. So kind of, you can think also about these functions, xa here as, well, Bartnik has harmonic coordinates. These are also some kind of coordinates on my asymptotically hyperbolic manifold that kind of come closest to harmonic coordinates. Yeah, maybe the idea would be like, I mentioned this hyperboloidal model of hyperbolic space in the beginning, hyperboloid sitting in Minkowski. So these functions are kind of, they resemble these functions which are given by restrictions of coordinate functions in Minkowski to the hyperboloid. Yeah, so kind of in this way, I mean, yeah, we have two bases of the same n+1 dimensional space, and that's, this way we get this boost A. Yeah, and then after that, it's one can identify the rest that it's close to identity. Okay, so we'll just switch it off. We can switch it on later if necessary. Yeah, so, well, covariance is again, it's also very similar to the smooth case. This is what Bartnik called miraculous cancellation. So when you change the chart, so magically you can collect all leading order terms into a divergence, and then difference of mass functionals is zero. So yeah, here basically, yeah. So we will assume that okay, boost part we can handle. One can just check how mass changes under the boost. But if you don't have it, so if you compute the mass using two different charts, then one can show that. Well, kind of leading order difference in this integral will be lead derivative of the hyperbolic metric, and then one can rewrite it as a divergence, of some one form, and because this one form will involve these functions Choquet that we have, this cutoff functions, so they are completely supported. So this will be zero, like bulk integral of versions of something completely supported. Yeah, so kind of mass functionals are the same if we don't have the boost component. Okay, and just lastly, a very quick comment on positive mass theorems. So of course it would be like nice to lower regularity in positive mass theorems using this definition, but kind of positivity part would be, I guess, feasible and not so difficult to do, because yeah, even like, I guess in all standard proofs, we argue kind of by smoothing out everything so that we can assume good asymptotics and good fall-off at infinity. And then kind of mass functional is continuous as long as it's well defined. So this is something that would work here. Yeah, but for rigidity part, we have no idea what to do. So we hope maybe, kind of the work that Lan and Dan Li has carried out on the rigidity of positive mass theorem, maybe it will shed some light eventually on what one should do in this case. Yes, so this is the end of my talk. Thank you very much.